My name's Todd Gooch, and my website's gravitationalunittheory.com. My book is G-Unit Theory First Revised Edition, and within it are some of my concepts about light. The first thing about light is that a photon of white light is composed of smaller photonic densities, the monochromatic colors, with violet being the most massive and red being the least massive of the photons. I've actually drawn the photons in the book. So if I can't find you a picture real quick, some of the work. Here's an example of indigo and violet. Blue and green, yellow and orange, and then finally the red's kind of hard to see, but nevertheless the way these are constructed has to do with the central circle or sphere and how many spheres around it connect with it at intervals of eighths between 0 and 2r. When you follow it down, the concentrations of the light become more and more dense, and thus this correlation here. Never took the time to actually count them and try and figure out what their exact ratio and densities are, although it's something that I've thought about doing. So these photons, what they do is they line up according to mass. Most massive ones in the center, least massive ones on the outside, and your photon of white light flies through space. Let's talk about space a little bit. Gravitational unit theory says that outer space is actually composed of the fabric of space. So the gravitational units are within the fabric, and the photon travels through it. And the idea being that just like a terminal velocity of a person that falls, say, from an airplane, they can only reach a maximum velocity because the air gets in the way. Again, this is what's going on with light. The so-called vacuum of space is composed of a fabric, which then it causes the photon to have a terminal velocity. The concept of the photon encountering a prism it elutes out according to mass is the idea. So the photon will impact the prism. This impacts the prism. The violet comes through first and bends the most because it's the most massive. And the next thing that happens, so violet goes a little further down, and the indigo, a little bit off trajectory, comes into play like this. The violet moves down a little more, the indigo moves down a little more, then the blue, at a slightly different trajectory, comes through the prism. The violet moves down, indigo moves down, blue moves down, and then it's the green's turn to come through, eluting through by mass, just as if it was a sample going through an elution through a glass-packed column. So the way I look at this is that the masses are causing an elution effect upon the impacting of a prism. And that's how the rainbow is formed, from a photon of white light. I'd like to talk a little bit about the split screen experiment, which uses monochromatic light. So to use one of these photonic densities, they usually use red, which is way down here at the end, although you do see some green, more green lasers and that, but generally you see red lasers that they do the experiments with. Well, as I go back to my book, it's hard to see the red, but it's very close to this drawing here of the orange, which is very not very dense at all. It's very least dense, basically, as opposed to maybe something like violet or indigo. So what they do is that they have the monochromatic light come through, and they'll have a split screen. And what will happen is that as the light hits it, it causes a diffraction pattern of lights and darks on the back wall. The idea being that it's behaving in a wave fashion, and at these nodal points, it's impacting the second screen. Well, then what they did was they made the aperture on a second split screen to be, they consider to be the smallest possible wavelength of the light, so that only single photons can get through onto the back wall should they be coming through like this. And then the idea is they are supposed to hit the back wall because the wavelength of light is that of the photon, and then therefore this is what they expect. But what they see is, again, they see this type of thing happening here on the back wall, and they can't figure it out. And it's obvious to me that that the reason for this is that these densities that I have are far smaller than the apertures. So they think they know what a photon is, but really they may only know what a photon of white light is. This is definitely different light, and it's predicted to go way down, possibly all the way down to the G unit level, which is times 10 to the negative 36 meters. It's probably far smaller than what they're giving it credit for being here. They may not be able to actually make an aperture that's so small that they can just get a single photon, and they aren't going to travel. Photons aren't exactly predicted to travel like baseballs. They travel as a density. So there's a lot to be learned by looking at the physical model that I've drawn using using physical geometry. Thank you.